just email me and ask me to record it, okay? So I'll remember to do that. Okay, can you guys still hear me? All righty. Something's weird. Can you guys see me? You can't see me. How about now? Can you see me? Okay, I think that's got it. Okay. All right. So I'm going to go through, we're going to talk about thermal physics a little bit. Then we're going to stop and do a little mini lab, and then we're going to do some problems. Okay. So we're going to keep going. We use the exact same notebook you've been using from last semester. We're just going to keep going. We finished Unit 6, so we're going to start Unit 7 now, all right? So in a second here, as soon as you see my presentation, give me a thumbs up. You guys see something on the screen there, presentation? All righty. So unmute yourself and break in and say hi and get my attention if you have a question, because I can't see everything all at once when I'm presenting, okay? All right, so here we go. Something's wrong. All right, so we're going to look at what is called thermal physics, okay? So the first thing to do is talk about temperature. And people knew for a long time that there was this sort of measurement of temperature. You can put your hand on a rock and you can tell whether the rock is hot or whether the rock is cold. The problem is, if you're trying to do experiments, how do you exactly measure how hot or cold something is? So you need what are called reference points. You need to all agree. And initially, people were looking for some reference points that were the same. So they found out that the internal temperature of a horse turns out to be pretty much the exact same temperature. It doesn't matter whether you have a horse in Australia or a horse in Russia or a horse in England or South America or United States. All horses' internal temperatures are all about the same. And that's true whether it's cold outside or hot outside, whether the horse has been running or sleeping. And so people use the internal temperatures of mammals as a reference point. They're fairly stable. Now, you guys know that if you get a fever, your temperature changes a little bit, but your temperature is about 98.6 most of the time. So that's a good stable temperature point. So it turns out the Fahrenheit scale was referenced on these stable temperatures. So 100 degrees is about the internal temperature of a mammal. And so that was one point. The other point that was used was the temperature at which seawater freezes. Now, water freezes at 32 degrees, right? If you guys are driving your car and it's drizzling and it's 31 degrees, you know to be careful because the water's probably going to start freezing. But that's pure water. You may know from chemistry that salt water freezes at a lower temperature. So it turns out that if you have seawater, it freezes at about 0 degrees. And so that is what we call the reference point. So we ended up with this temperature scale called Fahrenheit. And the Fahrenheit temperature scale was based on mammals and frozen salt water. Now, it turns out if you do that, you get some odd things. For example, water boils at 212 degrees. And that doesn't seem to be very useful. Also, as we got more accurate, it turns out that the temperature at which a horse's internal body was fluctuates too much. Even 1 or 2 degrees is way too much for the accuracy of our science. So we need a better way. So along came the next scale, which is called the Celsius scale. And the Celsius scale used water. The boiling point of water was called 100. And the freezing point of pure water was called 0 degrees Celsius. Okay? And most of the world now uses Celsius as the temperature scale. A couple places in sort of common usage, like on the Weather Channel and stuff, they use Fahrenheit. So that is England and the United States. But even in England and the United States, in science, we use Celsius as our temperature points. And then later on, some absolute temperature scales were developed, which I'll talk about in a little bit. Okay. Now, if you want to be able to convert between the temperature in Fahrenheit and the temperature in Celsius, you've got to find some sort of model. So here's what we know. When the temperature in Celsius is 0 degrees, the temperature in Fahrenheit is 32. So I'm going to plot that point right there, 0 and 32. The temperature in Celsius is 100 degrees, so that's the boiling temperature of water. In Fahrenheit, that's 212. So there we go. So if you want to know what is the mathematical model, all you got to do is find the slope of this line, and you got to find the intercept of the line. Well, the intercept's pretty easy. Where does it cross the y-axis? It crosses right here at 32. So the intercept is 32, and it turns out the slope is 1.8. So I won't bore you with too many details, but this turns out to be your mathematical model. All right? And that actually allows us to convert any temperature in Celsius to a temperature in Fahrenheit. So go ahead and flip to the back of your notebook. Make a new toolbox. This is Toolbox Unit 7. And for your toolbox in Unit 7, you can put this equation in there. We're going to use capital T for temperature, and then there's a subscript for F. So the temperature in Fahrenheit is equal to 1.8 times the temperature in Celsius plus 32. All right, everybody got that? Grab your calculator. We're going to have a little bit of participation here. Do a calculation. I'm going to have you unmute yourself and tell me what you got, okay? So if the temperature in Celsius were 40 degrees, what would be the temperature in Fahrenheit? The temperature in Celsius is 4 degrees. Would you go to school that day? What's the temperature in Fahrenheit? Got it there, Lexi?
39.2.
I think something went wrong there. The temperature in Celsius is 40. So you got to take 1.8 times 40 and then add 32.
104. I did Celsius for 4 degrees, not 40.
Oh, 4. I don't. Yeah, that's about right for 4. Good. So did you say 104?
Yeah.
All right. So if your thermometer is on Celsius and it says 40, you should be staying home from school that day, right? It doesn't really matter because you guys stay home every day, but you know what I mean. All right. What if the temperature was minus 20 degrees Celsius? The temperature in Celsius is minus 20. What would the temperature in Fahrenheit be? Evan, you got an answer there?
-4.
-4. That's right. Yep. Good job. Okay, so you guys see how to do that? Now, what if I said, hey, the temperature in Fahrenheit is 72 degrees. If the temperature in Fahrenheit was 72 degrees, what would the temperature in Celsius be? What do you think? Carly, you got it?
Did you say 72?
72 is the temperature in Fahrenheit. So what would the temperature in Celsius be?
I got 23.3. I'm not sure.
Why do you like that?
Huh?
It's right.
Oh.
It's right. Why don't you like it?
I don't know. It wasn't like an even number, so I just didn't know.
Oh, yeah. So my room right now is about 23 degrees Celsius. About 72 degrees. Okay? All right. So you got that in your toolbox, right? So you can convert back and forth. If you want to, instead of using 1.8, you can use 9/5. It's the same thing. So the temperature in Fahrenheit is 9/5 times the temperature in Celsius plus 32. And then if you solve this equation for the temperature in Celsius, you would subtract 32 and then Instead of multiplying by 9/5, you'd multiply by 5/9. So this is the same equation solved for the temperature in Celsius. So that's what Carly just did. Okay, so if you want to write that in your toolbox, you're welcome to. It's really the same equation. 9/5 is 1.8, but maybe that'll help you. I don't know. All right. So that's how we convert temperature. We already did that one. Now, it turns out, hang on one second. It turns out that a guy by the name of Robert Brown discovered that if you sprinkle pepper on water, and there used to be a video here, it's no longer linked. I got to find a new video. But if you sprinkle pepper on water and you watch it with a microscope, you'll notice the pepper will just jiggle around a little bit. It jiggles back and forth, back and forth, back and forth. And so what Robert Browning realized is water in a cup is actually in motion. The molecules are moving all around, okay? And so you may remember when we made our big bubble chart. You guys remember our big bubble chart? We made of all the forms of energy that we had all those little circles everywhere. One of the forms of energy was thermal energy. So it turns out that thermal energy is the energy of all of the atoms that are in motion. So all the atoms in a cup of water are in motion. Because they're in motion, if you sprinkle something really light on them, like pepper, they'll knock the pepper around, and the pepper will actually jerk around in the water, and you can see that under a microscope. So they all have kinetic energy, and they have kinetic energy because they are moving. They have kinetic energy because they're spinning, so water molecules are actually these complicated hydrogens with two hydrogens attached to an oxygen, and they're spinning. And they also kind of, the hydrogens kind of bounce away from the oxygen like they're on springs. They kind of bounce back and forth, and so they oscillate, we say. So those are all ways that they have kinetic energy, they're moving, okay? So kinetic energy associated with molecular motion is what we're gonna call thermal energy, all right? So don't panic, I've got this on the next slide. Here is what I need you to jot down in your notes. This is the big idea. The thermal energy is the kinetic energy of all of the molecules added up. Thermal energy is the kinetic energy that is associated with the motion of the molecules. All right, you good? Now the other two you don't need to write down. Heat is actually going to be the transfer of thermal energy from one form to another. So heat is something that transfers. You can get heat from something that has lots of thermal energy, or you can lose heat, but you don't really have heat. You have thermal energy. Heat is the transfer of it, okay? And lastly, temperature is going to be a measure of this thermal energy. It's going to be a way to measure how much energy the molecules have as they're moving around. Okay, now I want to talk about pressure really quickly because we're going to use it in our little mini lab here. Okay, so let's suppose I have a container. Can you guys see my box here? These little molecules would all be in motion. They'd be jiggling around. And some of them would be smacking into the side of the container. When they smack into the side of the container, they push on the container side. And there's billions and billions of these inside, all pushing on the container. And if I took the force they exert and I divide it by the area, I would get the pressure. So when we talk about pressure, you can really just think about it as the force of the molecules smacked into the wall. Is that so? If you say my tire has a pressure of 32 pounds per square inch, what you're really measuring is the force of all the molecules inside smacking against the wall of the tire and pushing it outwards. Okay, that's what pressure is. So what we're going to do is we're going to do a little experiment where we're going to look at pressure and temperature. And so to do that, we're going to come back to me here. Can you guys see me now? I'm not big. Go ahead and pin me to your screen so I'm big. I'm going to walk over to the lab area, and we're going to do a little experiment. You got a piece of paper or a pencil to jot something down? All right, so here we are at the back of the room. Give me a thumbs up if you can see a beaker of boiling water and you can hear me okay.
My computer is about to die and my charger is not working. I don't know why.
Uh-oh. I'm recording it, so you can come back and watch it if you die. All right, so here's what I've got a gizmo right here, and what it has is a bulb. It's a metal empty sphere. It's filled with air, and it's connected to a pressure meter. So right now, the pressure meter is measuring the force of the air molecules bouncing against the wall. Did I lose you guys? I lost Maddie. Who's there? Are you guys still there?
Yeah, I'm still here.
Evan, are you there?
Yeah, I'm here.
Did you guys see me okay?
Yeah.
Yep.
Okay, somehow I lost everybody's video feed, but you guys can still hear me and see me.
Yep.
Okay. All right, so here's what we got. This measures the pressure. What I'm going to do is stick it in the boiling water. Okay? So now it's in boiling water. And I don't know if you guys can see, but the pressure is going up. This gauge right here measures the pressure. Okay? We're going to let it go up a little bit there. And so here's what we got. So this is what I want you to jot down. When the temperature is 100 degrees for boiling water, so I got boiling water here, the temperature is 100 degrees, the pressure is 18.5 pounds per square inch. You got that? So that's one of our data points, 18.5. Now, I'm going to take it out of the water, boiling water, and you guys might notice that as it cools, the pressure is going down. So as the molecules in here are moving slower and slower, they don't hit the wall as hard, and the force is going down. What I'm going to do is now stick it in a bucket of ice. So this is a bucket of ice water. Maybe you can hear it. And what you can see is that it's dropping. The pressure is dropping. As the molecules move slower, they don't smack into the walls as hard. And Evan, do you think you could read that scale? Can you read that pressure there? Is it clear enough?
It's very blurry, but just under 15. I think that's 14.
Yeah, it's right on 14 right now. And now it's about 13.9. Okay, is this still blurry? All right, so what we have is about 13.9. And you guys wrote down the other one, right? I hope. All right, so what we're going to do is we're going to see if we can plot those. Carly, are you still there? Okay, you're coming back to me now. Nope. The internet's all loaded down. All right. All right, so here's what we got. We have two temperatures and two pressures. So what I want you guys to do is go to desmos.com, desmos.com. Go to desmos.com, and when you get there, click on Graph and Calculator right in the middle. And then you should have a screen that looks something like mine. Okay, is that working? You guys? All right, Maddie, is it working for you? You got to unmute yourself, guys. I can't see anybody anymore.
Mine's still loading. It's taking a second.
Okay. Evan, are you good?
Yep, I got it.
And you can see my screen?
Yep.
All right. There, how's it going there? Is it working?
Yeah.
Okay. All right. So, Maddie, even if yours is still loading, take a watch on mine really quickly. What we're going to do is we're going to put in our 2 points. Okay. So, watch me first, and then I'll give you a minute to do it yourself. The first point, X was 100, the temperature was 100, and the pressure was 18.5. And then I'm going to put a comma. My next point was when the temperature was 0, the ice water, and it was 13.9. Those are our two data points. And they're not going to show up on the graph yet, so you'll have to zoom out on the graph to be able to see those data points. So there we go. I can kind of see them now. Go ahead and try that. You got to put parentheses around each data point, and you got to put a comma between them. So see if you can plot those points. So when the temperature was 100, the pressure was 18.5. When the temperature was 0 degrees Celsius, it was 13.9. So you should have 2 dots on there. All right, I can see some of you again. Give me a thumbs up when you got your 2 dots on there. Evan, I see you. Andres, I got it. Lexi, you got it yet? Carly, you still with us? Is this like your car? The gas light goes on, but you can still go forever?
It's on 3%. I'm thinking it's my computer again, even though I already got a new one, because I have 2 chargers with me and neither of them are charging my computer.
Weird. All right. Okay. Now, what we want to do is we want to find the equation of that line. Okay. So, can you guys use those 2 points and find the slope? y2 minus y1 over x2 minus x1. Go ahead and see if you can find the slope. All right. Let's see. Andres, you got the slope there?
I haven't simplified it yet, but almost.
Okay. Just get a decimal form.
All right. I got 0.046.
That's it. Everybody get that? Good. Now, Andres, what's the intercept? Where would the line that goes to those 2 points, where would it cross the y-axis?
At 13.9.
Okay. All right. So everybody watch my screen now. I'm going to show you how we do this. Down below here, I'm going to click in the next box. I'm going to write the equation of the line, which is y equals 0.046 is what Andres got. So it's y equals mx plus the intercept, which was 13.9. If you guys put the equation of the line in that next box, it should show up, and it should go through both those points. Okay? See if you can do that. Try to type the equation and see if it shows up on Desmos there. All right, got it? All right, now here's what we're gonna do. Did you guys notice that as the temperature got lower, the pressure got lower? Yeah? And the reason we have pressure is because we have molecules bouncing against the walls. So as we cool it, the molecules move slower and they didn't push as hard. What we are gonna do is try to figure out what would happen if we kept getting colder. So I'm gonna go up to the little wrench up at the top right corner here, and I'm just gonna change my Y scale. I'm gonna make my Y scale go from like -5 to maybe 20. That just changes the Y scale so it looks a little bigger. And then, watch mine here. I'm gonna ask, if I kept cooling it, the pressure would keep dropping, right? If I keep cooling it, keep cooling it, keep cooling it, at what temperature does the pressure get all the way down to 0? So see if you can do that on yours. Scroll over to the left and see where's your line cross the x-axis. At what temperature would the pressure be all the way down to 0? Oh, there, can you see there? What do you have? What's the temperature when the pressure gets all the way down to 0, where it crosses the axis?
302?
302?
Yeah.
I think, is it negative?
Yeah.
Yeah. All right, so what that means is if we keep cooling the air molecules, eventually they're gonna stop moving. And if they stop moving, they won't push on the walls at all, right? So if temperature measures the energy, can you get any colder than when things are not moving? You can't. When things stop moving, when the pressure is 0, that's as cold as you can get. We call that absolute 0. And absolute 0 is somewhere close to -300 degrees Celsius. Okay? If we kept cooling our bulb, our metal sphere, when we got to -300, the pressure would be 0. The molecules would not be moving. And when the molecules aren't moving, you can't make them go any slower. Okay? So that we call absolute 0. All right? All right. Do me a favor and take your Desmos screen, shrink it so you can see your 2 points and your intercept over on the x-axis. Take a screenshot of it, and we're going to turn that in for some free points. So you're going to upload your screenshot as Lab 1. If you were in class, you'd be doing this at stations with a graph paper and plotting it, but you guys are virtual, so you get the short version. So just take a screenshot of your Desmos graph that has both your points on it and your intercept, and we're just going to upload that for our graph, okay? Take a minute to do that, and then come back and we'll finish up. All right, give me a thumbs up when you got that uploaded, the screenshot uploaded. Give me a thumbs down if you still need more time. Lexi, all I can see is the top of your head. I can't see your hand at all. Maddie, I can't see yours either. Okay, need more time. Okay. Okay, so you need more time. It's okay. All right, give me a thumbs down if you still need more time. Okay, I think everybody's ready to go on. All right, can you guys see the presentation again now? Okay. So here's what you got. My graphs looks a little different because I did it in Excel instead of Desmos, but we have 2 points. When we cooled the gizmo, the pressure dropped. If we were to cool it all the way down here, it would drop all the way to 0. Now, we got about negative 300, but our equipment isn't great. It's carefully calibrated. If we use better equipment, it turns out that absolute 0 is actually about negative 273, not 300. Okay? So 273 degrees is the coldest we can ever get. Temperature is a measure of motion, kinetic energy, and you can't get colder than not moving. When things are stopped, they can't move any slower. So it turns out temperature doesn't go on forever. It has a bottom, and the bottom is at 273 degrees below 0 on our scale. Now, it seems silly to have a scale where 0 isn't 0. So we tend to use a new temperature scale called the Kelvin scale. The Kelvin scale is like the Celsius scale. It just starts all the way down there at the bottom. Okay, so instead of starting here at 0, it just moves 0 all the way down here. So this is 0, and then water will freeze at 273 above 0 on the Kelvin scale. Okay, so the absolute temperature in Kelvin is a measure of how much energy it has. All right, that's the kind of the short story. So put this equation right here in your toolbox. So the temperature in Kelvin is equal to the temperature in Celsius plus 273. We'll do some conversions there sometimes. All right. Have you guys heard of absolute 0? Who's had chemistry? Give me a wave if you've had chemistry. Yeah, so most of you have had chemistry, so you've heard of this before, right? This is not new. The thing that you don't really make the connection with in chemistry is that temperature is really just kinetic energy. All right, good. So I'm going to skip that one. I want to show you another demo really quickly. So let me zoom over to my demo. Actually, I'm going to bring it here because when I go over there, I lose you guys. So, all right, you guys see me back? Okay, give me a second to get my stuff. All right, so if you're not in person, you can't actually do it yourself. It feels a little bit like magic, but here's what I got. I got a ring, and I got a ball, and the ball fits through the ring perfectly. Okay, so it's a ball on a stick and a ring on a stick, and the ball fits through the ring. Okay, see that? It's close. You don't see a whole lot of extra room in there, right? It's a very close fit, but it fits through there. Now, what I'm going to do is take my blowtorch, and I'm going to heat the ball. So here goes. I'm going to heat this ball. So what I have is chemical potential energy being converted to thermal energy, and that thermal energy is going into the ball, and the ball is getting hot. And if I wait just a minute or two here, so now I've got the ball really hot. Now it's starting to get tight. We're going to heat it a little more. Okay, now it's getting pretty hot. And you'll see it doesn't fit through anymore. See that? I know it doesn't feel like much when you're watching it on the screen. If you were here, we would pass it around and you could try it. This ball will not go through the ring anymore. That's as far as it goes. Okay? It doesn't go through anymore because it's hot. So what happened is the heat is making all of the molecules in here move a lot faster. And because they're moving faster, they take up more space. They get bigger. This is called thermal expansion. When materials get hotter, they expand. It's not a whole lot, but it's enough. If something is pretty close to start with, it's enough to make it so that it won't fit through anymore. Okay? So we call that thermal expansion. All right, I gotta set this down now. Okay, I had to find somewhere safe to put it. It's a couple hundred degrees. All right, so that's called thermal expansion. Have you ever seen these on the roadway? When you're driving along, especially near bridges, sometimes you see something that looks like this. That is a thermal expansion plate. When the road gets hot in the summertime, it expands. And if it didn't have somewhere to go, it would buckle. And so these plates are built in with teeth. When it's hot, the gaps are closed. And when it gets cold, the big sections of road shrink and these guys spread apart so they barely overlap. That way you don't get a big bump in the road when it's hot or cold. So that's an example of thermal expansion. When you build bridges, you've got to leave one side to slide. When you have windows in your house, the windows of your house don't go all the way up to the edge of your house. They're actually got a squishy material around them called caulk. Caulk is squishy silicon. That way when your window shrinks and gets bigger and smaller when the temperature changes, it doesn't crack and break. It has some room to give. That we fill your teeth with stuff that expands at the exact same rate as your tooth. You'd really hate to have somebody fill your tooth if you got a filling, and that filling expands faster than your tooth does when you take a drink of a hot fluid, like a cup of tea. Then your tooth would crack. So these are all examples of thermal expansion. The most famous example is probably a thermometer. If you have some fluid in here, usually we use a red alcohol. When it gets warmer, it takes up more space. Since it has nowhere to go except up this little tube, it moves up the tube. And you can make little marks on the tube, and we call that a thermometer, right? So a thermometer works because as the alcohol gets hotter, it takes up more room. It pushes up the tube. So that's an example of thermal expansion. If you go out and look at the railroad tracks, every quarter mile or so, you'll see there's a splice like this. You can't have two railroad tracks just butt up against each other because then there's no room to expand. So there's two slices that are kind of like triangles so that as the track gets longer, they slide past each other right here. Okay? And you can make things that look like this. There's a little drop of mercury here. This is an old-fashioned thermostat. When things get hotter, this coil expands and it actually tips this little guy and makes the little droplet of mercury slide over to the right. And when it slides over to the right, it turns the switch on. And that makes your heat come on. So that's another example. So the short story is that when the temperature increases, the distance between the molecules gets a little bit bigger. It's kind of like if we were going to pack 100 people in a room, that would be easy if everybody stood still. But if everybody started twitching and moving, jumping around and dancing, you wouldn't be able to fit them all in the room. They would expand outwards, right? They'd flow into other rooms. So when objects are in motion, the faster they move, the more space they need. So things expand as they get bigger. Now, this is true for most substances. There's only a couple of exceptions in nature, and one of them is water. Right when you start to freeze water, it doesn't actually contract. It actually expands a little bit. Have you ever put a can of soda in the freezer? Come on, admit it. What happened, Evan?
It expanded and got exploded.
And broke the aluminum can it was in and made a huge mess, right? Yeah. You don't believe me? Try it at your science lab for the afternoon. And then your homework for the next 3 days is cleaning up the mess in your freezer. So ice, right when ice freezes, it expands a little bit. That's an exception. Almost all of nature works the opposite. As things cool, they get smaller. Okay? So here's the equation we're going to use. You can go ahead and put this in your toolbox. This tells us how much the length of something will change. So delta L is the change in the length. It's how much the length changes. So delta X is the change in length. L0 is the starting length. It's how long something is to start with. Alpha is a number which tells you how much each material will change length. It's called the thermal expansion coefficient, or the coefficient of thermal expansion. And we're just going to look that up in a table. I'll show you in a minute. So this symbol right here, it's what's called the Greek letter alpha. It's kind of like an A, but it's got kind of loopy sides. It's kind of like a fish, actually. If you've seen the fish that on the side that people use, symbol fish unity times, that's the symbol. It's an alpha. And then delta T is the change in temperature. And it's always going to be in degrees Celsius. So if you get a problem and it's not in degrees Celsius, you got to convert it to degrees Celsius first and then solve the problem. All right, so got that in your toolbox? Give me a sideways thumb if you need more time. You good, Maddie? All right, good. So let's solve an example problem with that. First of all, let me show you the table. This is the table. It's linked in your homework. You'll always have it. Please don't ever memorize it. If you're working with aluminum, this is the number right here you're going to use for alpha. This alpha, oops. This alpha thing right here, you just look up in the table. Okay? So if you're using glass, we're going to use 9 times 10 to the negative 6. If you're using steel, you'd use 1.1 times 10 to the negative 5th. Okay? All right, so here's an example problem. I've got a picture window that overlooks the lake. This is, of course, in my dreams. A, I don't have a house on the lake, and B, I'm a teacher in New Pal, and there are no lakes. If I had a picture window and it looked over the lake, it might be 3 meters long. Okay? Oops, I forgot to put that in there. This should be 3 meters long. So find the change in the length of a 3.0 meter wide picture window. There we go. All right, so it's 9 feet wide. It's made of ordinary glass, and the temperature is going to go from 70 degrees Fahrenheit down to negative 10. So 70 is a nice warm day in the sun, and negative 10 is a really cold night when the Arctic blast comes in. Okay, so looking at the table, help me here, Maddie. What coefficient am I going to use for this problem? That little alpha thing, what value is it going to have? You got to unmute yourself, Maddie.
Would you use the glass? I don't know what.
Yep. Now there's 2 glasses, so which one are you going to use?
Ordinary.
Right. And what would that value be?
9 times 10 to the 6, negative 6.
That's right. So because we're using ordinary glass, we're going to use this value. If it was a steel railroad track, we would use the one for steel. So that's all you're going to use the table for, okay? And you don't ever need to memorize this. You will always have the table in your toolbox. All right. And don't even write the table down. I'm going to give it to you every time you need it. All right, now, the next thing you got to do is you got to convert your temperatures from Fahrenheit to Celsius. So let's see. How about Lexi? Can you convert 70 degrees Fahrenheit to Celsius? And Ozair, can you convert negative 10 degrees Fahrenheit to Celsius? Go ahead and do those conversions, and then when you got it, just unmute yourself and tell us what you got. And the rest of you go ahead and get them and check them, because I might call on you too. Got it there, Lexi?
Yeah, 21.1.
That's right. 70 degrees Fahrenheit is 21.1 degrees Celsius. So that is the initial temperature. Ozair, you got the negative 10 converted?
Is it negative 23?
It is. That's right. Negative 23. So here's what we have. I convert my temperatures, and we get 70 becomes 21. Negative 10 becomes negative 23. And so it starts at 21, it ends up at negative 23, that's the final. So now we can use our equation. Our equation says to find the change in length of my window, I take the starting length times alpha, which is what Maddie told us, the 9.0 times 10 to the negative 6, times the change in temperature, which is T final minus T initial, which we have from Ozair and Lexi. So when we put this all in, we can calculate delta L, the change in the length of the window. Okay? And that turns out to be about 1.2 millimeters. Now, 1.2 millimeters is not very big, is it? It's not like you're going to notice the window go from 9 feet to 10 feet. The changes are pretty small. But if you didn't build in something squishy, when your window shrinks 1.2 millimeters, that's a pretty big crack. And you would definitely notice it if there was a cold Arctic wind blowing in a crack that was 1.2 millimeters. 1.2 millimeters is about the thickness of a ruler. So you definitely don't want to crack that big in your house, right? But you can't shove a piece of wood in there, because then when it got warm the next day, it needs to expand. So we actually use a squishy stuff called caulk, which is basically silicone, which can bend and give as your window shrinks and grows. That's why your windows are caulked in, so they can grow and shrink with the temperature changes. Okay? All right, so you're going to solve some problems with this. There are two kinds of problems on the problem set for homework. The first kind of problem is just temperature conversions, and you can just use your calculator. The second part are problems that involve changes in length, and you're going to just kind of do your conversions, show me the equation, plug in your variables, and get your answer, okay? Does that make sense? All right, so that's the assignment for today. Do me a favor and just make sure you log in, solve the first problem so I know it's working for you, and you can log in and check your answers. And once you first one right, you can check out and work on those. We're going to do a lab tomorrow, so you should plan on having this problem set done by Wednesday, okay? All right, I'm going to go ahead and stop recording now. So just do me a favor and stay on till you get that first one right. And then you can head off to wherever it is you go and keep working on them on your own whenever you want to, okay?